Hello again, everyone. In the last video, we talked about product segmentation, and ABC analysis was the primary method to do so. Again, there are three types of items: A items, B items, and C items. Each product is grouped into one of these three item categories, with A items being the most important, then B, then C. Let's now talk about the distribution of sales volume of these products. If we were to walk through any retailer like Target or Walmart, we would see thousands of products. So possibly over 10,000 types of products or SKUs, probably hundreds of categories. For example, dry foods, frozen foods, cleaning equipment, clothing, etc. The important question I posed at the end of last video was how would the sales volume distribution look like for these SKUs? Would it be uniform? Would it be normal? How would that look like? For simplicity, let's just assume that we own and operate a single Quickie Mart. So this is the Quickie Mart from The Simpsons, and there are only 10 products that we sell in the store. So this is the 10 items sold in our fictitious store. We have some donuts, hot dogs we actually learn later that are made of tofu, Duff beer, some squishy, chips, milk, t-shirt, ice cream, stickers, and gum. And these are the only 10 items in the store. For each one of these fictitious items, we also have a fictitious SKU. So I made up these fake SKUs, and we want to see how the sales volume of these SKUs look like for any given week, month, or year, any given time period. If all of the items have the same sales volume for any given time period, then we would have a flat distribution or a uniform distribution. So if we were to draw a histogram of the sales volume for each given SKU, it would look something like this. And this is my histogram. The frequency is on the y-axis, the sales volume, and the SKU. So you would have 10 of these, right? Now, if we were to plot now the percentage of total sales volume with respect to the percentage of SKUs, then it will look like a diagonal line like this. So the way you interpret this is, as we add more SKUs, we have a total of 10 SKUs. They make up a small chunk of your total sales volume. So since every single item has the same sales volume, it contributes the same proportion to the total sales volume. The distribution could also be non-uniform. So in the last case we looked at, we assumed that all the SKUs have the same sales volume, but that's not necessarily the case. In pretty much all applications, it won't be the case. So if I were to now sort these SKUs based on sales volume and plot the histogram, then it would look something like this, so the first highest selling SKU, I have a bar here, the next highest selling SKU, I have a bar like this, the next one over, etc., and you'll have 10 of these. Now if we're to take the same histograms, the same distribution, and plot now the percent of total sales volume respect to percent of SKUs, then it would have a distribution that looks something like this. Now let's try to understand what this distribution implies, or how we derive this distribution. The first SKU, the highest selling SKU, has the highest contribution to the total sales volume. So if you were to kind of match this here, it's going to have the biggest contribution. The next one is going to have the next highest. So if I were to kind of look at the change in Y, you see how much higher this first one is with respect to this second one. Right. So for each additional SKU, it's going to have lower sales volume. So its contribution to the total sales volume is actually smaller. It turns out that in many settings, the distribution of sales volume tends to have the shape which closely follows the power law. A large percentage of your sales volume is only made up of a small number of SKUs. So in this case, you can see that only initially a very few SKUs make up a huge portion of your total sales volume. This would also be true if we were to look at revenues, profits, or some other metric. The power law is not unique to just product sales volume. We see this phenomenon in many other applications in both physical and social systems. And here are some examples The first example, Kleiber's law, states that the animal metabolism rates actually scales to the power of 3/4 based on an animal's mass. So for example, if you have a cat that's 1,000 times more massive than a mouse, the metabolism rate of that cat is approximately 32 times as high as the mouse. And in this law, it turns out that the frequency of a word in any language is inversely proportional to its frequency rank. So for example, the second most frequent word occurs half as often as the most frequent word. The third most frequent word occurs 1/3 as often as the most frequent word, etc. So what this implies is that you don't have to know too many words to actually become fluent in any language. In Pareto's law, this is the famous Pareto, it turns out that 80% of all income in a given population is held by just 20% of the population. And the power law also, if you think about it, this also applies to the diversity of products or the long tail. If you look at if you look at the modern e-commerce right now, the reason why Amazon's been so successful is their ability to cater and exploit this long tail. So this whole power law really points to this a few very important versus a trivial many. You have a few items that are disproportionately important to you versus the many numerous other items that individually make a very small contributions. If we now go back to the 10 SKUs in our Cookie Mart, we can roughly estimate the distribution of the sales volume of our SKUs. Let's assume that the measure that we're actually interested in is the annual revenues generated for each of these SKUs. We can calculate the annual revenues for each SKU by multiplying the price with the annual demand. So the sales price is just X, annual demand is Y, and the annual revenue is Z. So I got the Z column by simply multiplying X times Y. Once we have the annual revenues column calculated, we then need to sort our SKUs based on decreasing annual revenue value. So we're going to sort so that the values are decreasing. So in this table, we now have all of the annual revenues calculated, which was my Z column in the previous slide. It turns out if we're to sum up all of the revenues for all the SKUs, it's going to be 400,000 for the entire year for all of the SKUs combined. We're now ready to calculate the cumulative revenue column. You can think of this as the running total of all the revenues. So let's start with the second SKU, D03. The cumulative revenue value is going to be 218,000 because that's simply the cumulative revenue of the previous SKU plus the annual revenue of the second SKU, 108,000. That's how we end up with 218,000. So the next SKU down, M06, its annual revenue was 62,400. So the cumulative revenue up to that point then is 62,400 plus the 218,000. That's how we end up with 280,400. So you keep doing this, and at the end, these two values should match, right? So the cumulative revenue should match the total revenue for the sum of this entire column. We're now then ready to calculate the percent annual revenue. So this is simply the cumulative revenue value divided by the total revenue, or the last value in your cumulative revenue column. So the 27.5% value comes from dividing 110,000 by 400,000. Let me pick this one right here. 70.1% comes from dividing 280,400 by 400,000. So the way to understand this is up to this third SKU, okay, 70.1% of your total annual revenue is captured by the first three SKUs. Okay, so you can kind of see where this is headed. We're now actually ready to classify our SKUs into those three categories, A, B, and C. Now I'm going to introduce some arbitrary breakpoints. So this will vary depending on the application organization, but we're going to set it at 75%, 95%, and the rest. So what that means is the breakpoint between A items to B items is 75% of the percent annual revenue, and the breakpoint from B items to C items is 95%. And I'll demonstrate that here. So 75% means our A items are going to capture up to 75% of all the values, the annual value. In this case, this is only 3 of the SKUs. The first 3 SKUs makes up 70.1% of the total value. Okay, the arbitrary breakpoint is 75%, so that the B items then is from the 4th SKU onto the 6th SKU. So 95% breakpoint means that we're gonna stop at this point here. Okay, so again, just 3 SKUs, so 3 out of 10, 30%, it captures 20% of the value. So 95 minus 75, that's 20%. And then we're left with the remaining C items. These 4 SKUs, which make up 40% of the SKUs, only capture 5% of all of the annual revenues. Let's now graph the percent of annual revenue with respect to percent of SKUs of our 10 SKUs in our Cookie Mart. And you can kind of graphically see which SKUs fall under the A items, which SKUs belong to B items, etc. So the breakpoint, arbitrary breakpoint from A to B item was 75%. So we know from our results that roughly 30% or 3 out of 10 SKUs make up the A items. So they capture up roughly 71% total of all the annual value, the annual revenues. The next set of B items, the arbitrary breakpoint was at 95%. So you see in the first A items, the change in Y is the entire 75%. The change in Y for the B items is only 20%. So 95% minus 75. These make up my B items, and again, only 3 SKUs fell into that. And then the rest, the C items, only make up roughly 5% of the annual revenues. So these make up the rest. So this is a very small, simple example of ABC analysis. If you want to see a bigger example with more SKUs, you can look at the next video. So this is ABC analysis, again, is a very, very simple, useful way of segmenting products. Thank you.